Hello, my name is Nataliia Neshenko. I am PhD candidate in Florida Atlantic University, College of Engineering and Computer Science, working with Professor Furht and in collaboration with Professor Bou-Harb from the University of Texas in San Antonio. Today, I'm going to present our behavioral-based forensics investigation approach for analyzing attacks on water plants using GANs. I first will provide the background and motivation behind this work, go over the related research in the field, and demonstrate the added value of our work. Further, I dive deeper into the approach and its benefits and evaluation strategies, and present a couple of results to demonstrate this approach and elaborate on future extension and conclude this presentation. Water is most valuable resource on the planet, and this is why economic efficiency and quality are top priorities for the water industry, while they still remain challenging. The consistent end-to-end digitalization of water facilities supported by technological vendors helps the water and wastewater industry meet these challenges. So these industrial control systems, which provide partial or fully automated control for critical infrastructure, are now accessible through network communication and support economically efficient operations. But what appears to be a simple and efficient solution is not that simple. With ever evolving IT environment, the attack surface keeps expanding. And if adversary gained remote control over the automated operations, the fresh water supply and quality can be seriously compromised. This is unfortunately not a theoretical threat, and the first attack against network-connected water facilities was recorded decades ago in Australia, where around 120,000 people were put in danger by the polluted water due to the cyber attack. Cyber attack also can target water meters, and in order to manipulate the billing system and cause economic loss, which happened in Pennsylvania. And partially successful attempt to poison water was recently conducted in Florida. And these are not isolated incidents, but rather the example of many other attacks. Increased number of cyber attacks against critical infrastructure, vulnerable network accessible automated system of critical infrastructure and water facilities, and limited forensics investigation methods with asset attribution capabilities specifically for ICS deployed in water plants, motivated us to conduct this research and address these challenges. So we introduce a supervised method that fingerprints this system behavior under regular operation and infer attack and attacked ICS assets for their further prioritization and further prioritized investigation. Researchers around the world approach this problem from two different perspectives: control theoretical and data-driven. Data-driven includes various machine learning approaches, and one of them is generative adversarial network known as GAN. And there are also a couple of methods that can be employed for anomaly attribution or for ICS asset attribution. Control theoretical approach assumes the existence of mathematical model of underlying ICS. It basically takes ICS and converts it to this mathematical model, and then leverage it for attack inference and their investigation. Is it computationally expensive? Yes. Is it practical? Well, ICS deployed in various water plants can have incompatible structure depending on their types. For instance, domestic and industrial wastewater treatment required different filtering and different disinfectant technology, as well as advanced treatment, such as oil separation, removing toxic organic ingredients, and so on. Furthermore, ICS assets are prone to continuous modification, which requires thorough maintenance of the mathematical model and regular update. There are many other reasons that make obtaining and maintaining this mathematical model challenging task for control theoretical approaches. Given this, using the identical model-based attack detection technique for ICS deployed in different plans seems to be unrealistic. Therefore, our approach generalizes the underlying system by employing learning algorithm that operates on circulating ICS data. Many machine learning methods are employed to infer cyber attacks, and some examples of the employed methods include deep neural networks, support vector machines, autoencoders, dual isolation forests, and many others. For many machine learning methods, anomaly interpretation is a well-known issue, while it is essential feature towards prioritization for cyber forensics. And also attack-related data is rarely widely available due to security and privacy reasons. Therefore, our approach, we keep this in mind when we designed our approach, and our approach operates with multivariate data and can be trained only on attack-free instances. And it also pinpoints attacked ICS assets. One of the machine learning algorithms that we will employ actually in our work is widely used for anomaly detection across different domains, such as healthcare, public safety, finance, and network cybersecurity. And this network is known as generative adversarial networks, GAN. And different variations of underlying architecture unlock the potential of this network to learn underlying data in depth, so it can grasp the inherited dependencies between variables, which is a desired feature for ICS deployed in water plants. Our approach extends the application of GANs-based anomaly inference method towards cyber forensics in this critical domain. For methods that solely rely on empirical data, future importance, algorithms can serve as medium for attack attribution. Please note that feature, we call feature here its variable or its ICS assets. Feature importance refer to a range of techniques that rank the input variables of the prediction model, indicating the relative significance of each feature for prediction. There are numerous ways of deriving these ranks, and many algorithms sustain this purpose. And notable examples include, but are not limited to, decision trees, statistical correlations, and game theoretical models. Another method that appears in literature is to derive highest future-wise reconstruction error and its change ratio, and declare the assets under attack. The assets with highest ratio is asset under attack. However, given the stochastic nature of such technique, obtained estimates are subject to some degree of uncertainty. To this end, we perceive that the fusion of independent outcomes produced by each method would likely render better anomaly attribution and conquer the ambiguity of such attribution. To summarize, we frame our contribution as follows. We complement existing methods supporting cyber forensics for water treatment plants. And to this end, we introduce an unsupervised approach that infers maliciously modified processes and pinpoint attacked sensors. We leverage bidirectional GAN and recurrent and convolutional neural networks to fingerprint the behavior of ICS deployed in water plants and to isolate anomalies which represent ongoing attack and attribute attack by pinpointing the exploited ICS assets, which is essential function towards forensics prioritization. And we evaluate the approach on empirical data collected by small-scale water treatment plant. And the empirical evaluation demonstrate the equivalent or better performance in comparison with state-of-the-art. And we also show that the proposed approach can identify exploited ICS assets with nearly 15% accuracy improvement over prior literature contributions. There are three core components of our approach. It's behavior-based, behavior fingerprinting, attack inference, and attack attribution. The first component learns to fingerprint the typical behavior of the system. And for that, we leverage a bidirectional GAN-based learning approach, which we will discuss further. The second component estimates anomaly score by comparing incoming data sequences for each sensor or actuator with fingerprinted system behavior. And this score indicates any plausible attack. The attribution function evaluates the contribution of each asset to the anomaly score and extract the affected ICS asset to prioritize cyber forensics. To fingerprint the system behavior under normal operation, we employ a GAN-based model. And in classical formulation, GAN is generative and discriminative deep learning architecture that consists of two competing neural network known as generator and discriminator. As a first step, generator receives noise to learn its distribution. And based on perceived distribution, generator produces data samples and passes them to discriminator. In its turn, the network discriminator determines the distribution between real and fake data and back-propagates the probability of data authenticity to generator. Further, generator adapts its parameter based on received gradient information and passes new samples to discriminator. And they work together back and forth to meet their learning objectives, which is for generator is to produce more realistic instances, and for discriminator is to improve ability to distinguish fake data from the real. Our architecture is different from classical formulation, and it was inspired by the model which was widely and successfully used for detection anomalies and images. And this architecture consists additional network known as encoder, and encoder maps incoming data sequences to latent variable space Z. In this architecture, E should learn to invert the generator G. And this architecture actually proved under our investigation that it produced better results in comparison to classical formulation. For attack inference, we use generator and discriminator. First, network generator, because network generator was trained to capture the complexity of the data distribution and to generate sensors measurements at certain point of time. So we can take the latent representation of incoming data obtained from encoder and reconstruct the expected ICS behavior by using generator. The trained model then evaluates L1 norm distance, namely residual loss between actual and expected physical measurements for all ICS assets. We further utilize the ability of trained discriminator to distinguish the normal operational behavior of ICS. And the discriminator determines the distribution between fingerprinted behavior and latent representation of incoming data obtained from encoder. And it returns abnormality score, namely the discriminator loss. And we further obtain the regularity score for each time point is the weighted sum of both of these losses. As mentioned, for data-driven methods, the attack attribution can be made with future selection algorithms. However, independent results can be misinterpreted. We perceive that fusion of independent outcomes produced by each method would likely render the better anomaly attribution and conquer the ambiguity of such attribution. And for that, we use a degree, the notion of degree of belief that selected method correctly identified the assets under attack. And this degree is computed based on amount of relative support representing distance between prediction made by each combined method. And we declare ICS asset is asset under attack if its score is 75 percentile. For our approach, we selected three methods: classification and regression trees, sharply values, it's a game theoretical approach, and kernel sharp, which is model agnostic method for deriving relative future importance. Our approach has several benefits. It works with multivariate data and can explore inherited dependencies between ICS assets, which is desired feature for water plants, and this leads to better anomaly inference. It also learns behavior of the underlying system, so it's eliminate the need of mathematical model. It is trained on attack-free data, so it manifests its promising application for cyber forensics of ICS, where attack-related data is rarely available due to security and privacy reasons. And it also pinpoints attacked ICS assets and contributes towards cyber security and forensics prioritization objective. To evaluate performance of our method, we use data that collected by a small-scale water treatment plant, similar to one that can be found in smart cities. The data consists of 7 days of attack-free data and 4 days under different types of attack. Attacks can vary in time, attack sensors, attack process level. We seek an answer for the following question for evaluation strategy. Our evaluation strategy is follows. We seek answers for several questions. And first of them, how accurately does the approach fingerprint the behavior of underlying system by solely relying on empirical data? Into that, we evaluate how firmly our model does so. we employ discrepancy measures known as energy distance, denoted as ED, and maximum mean discrepancy, denoted as MMD, to the actual and reconstructed sequences. Lower ED and MMD measures indicate the lower discrepancies between two probabilities and suggest, after stabilization, the high quality of behavior fingerprinting. There are two other questions. How can the proposed approach correctly infer attacks? How well it does so, and how well it distinguish attack sensors. And for that, we use usual metrics: sensitivity, precision, and F1 score. As a prerequisite for anomaly detection, the proposed approach should carefully model system behavior under regular operation. This figure shows that largest decrease in both metrics which is maximum mean discrepancy and energy distance, occur after 30-second epoch. And it is reasonable to suggest that the quality of generated data is stabilized after this epoch. And we also employ TSNE analysis and observe significant overlap between the original and perceived data. And in figure, original blue color indicates original data, and orange color indicates perceived data. In this significant overlap indeed indicates that the proposed model was able to grasp the system behavior quite closely. The proposed approach also demonstrates equivalent performance, state of the art, while asset attribution is significantly improved. Now I'll give you a couple of examples of inferred attack and pinpointed assets. The attack window here in this chart is denoted with red color, and the inference mechanism precisely isolate the identified incident, and it's denoted with this blue bar. However, irregularity score is higher after the actual attack, which we call this recovery after attack. And dataset marks this recovery time as a regular operation. However, it is essential to infer the stabilization period for further investigation of potential impact on the system, since it may take longer than a long time, sometimes hours, and for ICS to return to regular operation. The proposed methods correctly attribute attack to the respective assets, and it outperforms the previous proposed methods. In this table, bold indicate that correctly identified ICS assets. In the next scenario, the proposed approach also identified this attack. This is attack and irregularity score, and correctly attribute affected sensor, while it raised false alarm. Despite this, our methods outperform the previous contribution anyway. To conclude, and aiming to support cyber forensics in the context of ICS deployed in smart water facilities, we complement available contributions and introduce a supervised approach that infers cyber attacks and reveals the attack assets for forensics prioritization. The approach has three distinguishing characteristics. It operates with multivariate data, which is highly desired in ICS deployed in water treatment plants. It trained using only attack-free instances, therefore avoid the problem of non-available attack-related data. and it identifies the attack points and thus can reduce forensics overhead in critical infrastructure realm. For the future perspective, we plan to extend evaluation using different variants of ICS deployed in real-world water facilities and investigate the effect of pattern instability, which can be found in water distribution system as variation of water consumption by consumer. And we also plan investigate additional information fusion approaches to calibrate accuracy of asset attribution. And finally, we would like to explore mediation methods given the knowledge about the exact attacked assets from this work. Thank you for your interest to our work and for your time.